When we left off, we were discussing mental addition, and I was asking you to look at 5 problems, complete them in your head, and take note of the strategies you used and try to apply names to these strategies. We had 39 plus 57, 68 plus 35, 66 plus 19, 545 plus 228, 186 plus 125. The first strategy we can discuss is called the leading digit strategy. This strategy works with most addition problems, and a lot of people refer to it as front end because we use the front of the numbers first. For example, with our problem 38 plus 57, we can look at the front, or the highest place value, our tens. We have 30 plus 50, and that leaves our ones in a group next to it. So we have 80 plus 16, which gives us, of course, 96. And then we have compensation. This is another powerful mental math strategy. In this example, we'd have 39 plus 57. What we would do, because it is addition, we can take 1 unit from the 57 and compensate, or bring it to the 39 to build 40, which leaves us with a second add-in of 56. 40 plus 56 is, of course, easy to do mentally, 96. We transformed the 39 plus 57 into 40 plus 56. Then we have the break and bridge strategy. If we use problem 2, 68 plus 35, what we would do is decompose the second add-in into a power of 10. And so we have 68 plus 30, and then we would add the 5. 68 plus 30 is, of course, 98, and then 98 plus 5 is much more easy to do mentally. We could visualize it by using a number line. Again, we would break the second number apart using an expanded form, then add one place value at a time. So we would start at 68, add our 30 to get to 98, then add our 5 remaining to get to 103. And we have compatible numbers. Compatible numbers involve seeing a pair of digits whose sum is 10. If we look at problem 5, for example, 186 plus 125, we have our compatible numbers, 180 plus 120, which is easy to do mentally, and that leaves us with 6 ones plus 5 ones. So our 180 plus 120 is, of course, 300. Our 6 plus 5 is, of course, 11, for a total sum of 311. So again, now you have 4 strategies to perform addition mentally. The strategy that you choose is simply a matter of preference. Again, each strategy presents a benefit. Some are easier for some, but not for others. But your goal as a future educator is to become familiar with all of them and present them, because the more varieties that you present, the more options someone has that works for them. Now that we've looked at some strategies that you would use for addition, let's look at some strategies that children would use. Think about a child who has not yet learned the standard process for adding. How would they add 48 plus 26? One method would be to add up by tens. In the young child's development of addition, we want to add up, but some children might begin multi-digit addition in the same way. So they might add up by tens from 48. Meaning we go from 48 plus 10 is 58 plus 10 is 68. To get to the next 10, which would be 70, we have 2, and that leaves us with 4 more to complete our second add-in of 26. So we add up by tens. This was a very common strategy many years ago. Use 10 as a bridge. 48, 58, 68, there's our 20, plus 2 is 70, plus 4 more, 74. Or we can break our second number apart. We would say decompose. Another example here of 48 plus 26. We would decompose it into our tens and our ones. 48 plus our 2 tens or 20 is 68. Then we would add our 6 more to get 74. We could again use the number line for this strategy, starting at 48, increase by 20, and then by 6 more. There's a pictorial representation. Or we can use partial sums. This is a lot closer to the standard algorithm, which we'll be covering shortly. If we look at this diagram here and our base 10 blocks, we have our 48 represented on the top of the algorithm, 26 on the bottom. So if we count just our tens, we have 6 tens and 0 ones. Then we could add all of our ones together. All of our ones would be 14. So we have 2 partial sums. Our ones and our tens plus our tens together would give us a total sum of 74. And a lot of children are familiar with money, and they can use money to compensate, much like we did in our example. Depending on the child, we have 48 and 28. We're close to a $50 and a quarter. So we would say 50 plus 25 are 2 close numbers to 48 and 28. 50 plus 25, 48 is 2 less than 50. 26 is 1 more than 25. So 50 plus 25 minus 2 plus 1. So let's slow down and look at this again. 48 is 2 less than 50. That's where our minus 2 comes from. 26 is 1 more than 25. That's where our plus 1 comes from. When we get to larger numbers, can we adapt the strategies that we've just covered? For example, 368 plus 574. We could break the second number apart. We could break it into tens and ones and hundreds. Our 368 plus 500 is 868. Add that 70, 938. Add that 4, 942. Once we have strategy and we've built some proficiency, we'll move on to algorithms. And a major goal of elementary school mathematics is for students to become computationally fluent. So that includes development of efficient algorithms for each operation. But again, I stress that the algorithm comes once you have an understanding of the concept. An algorithm is a single, clearly described method that works in all cases. So mastering the algorithm for all of the operations is a long and challenging process because you need to first understand how the numbers are being manipulated. And this first arithmetic book in Europe was published in Italy near 1500, and it described a new base 10 system and many different procedures for adding, subtracting, multiplying, and dividing. Because the base 10 was so new, there were a lot of different algorithms in use. And over the years, certain algorithms will say won out. The algorithms that we learned and you learned to add, subtract, multiply, and divide are not the algorithms, but they're four of many. And they're not universally used today. In different parts of the country and different parts of the world, different algorithms are used. If we think about how we used to add before base 10, let's think about the Roman numerals. We couldn't just regroup because it wasn't a place value system. So we would have to combine symbols and do some rewriting where it was efficient. So if we look at this problem, if you read this, the x, remember, represents a 10. So we have 37. What does the XLVI represent? Because it's not a place value system, this is 10 less than 50 plus 5 plus 1. So it's 46. So again, this isn't going to work the same way that our algorithm works. We'd have to rewrite digits instead of just regroup digits. Using the standard algorithm, how would we add 267 and 133? Well, in the context of our system, when combining these, we would be combining our 1s, our 10s, and our 100s. So in our algorithm, we would line them up vertically, so the 1s of our first addend are above the 1s of our second addend. The 10s of our first addend are above the 10s of our second addend, and the 100s of our first addend are above the 100s of our second addend. And another way to think about this is when we talked about expanded form, when we decompose that number in expanded form into place value. Our 267 was really 200s plus 6 10s plus 7 1s. So we really need to go back to our numeration and think about it like that to really understand the algorithm. We also have an alternative algorithm. Some of you are familiar with this. It's called the lattice algorithm. If we look at this, we have our two addends, 645 plus 728. And what we do is we create a lattice board. So we have a rectangle that is bisected diagonally. 5 plus 8, our 1s go in the bottom section of this rectangle. Our 10s are in the top. 4 10s plus 2 10s, again 6 10s. So our 10s are in the same diagonal as our 10s from our first place values being added. We have 0 hundreds, 600s plus 700s, 1300s or 300s, and 1000. So again, we're adding up our place values, and then for each diagonal we find a sum. 3 is the only digit in this diagonal. 1 and 6 added together would make this diagonal a 7. 0 plus 3 is 3. 1 is alone in this place value, so 1,373. First, you write the problem. Below each place value, you draw a square, cut a diagonal through each square, and third, write the results of each partial sum in the box.